Good afternoon. What I want to talk about this afternoon arose out of a conversation I had with young Chris Gorse just over a year ago, just before the last SEEDS conference in Leeds. And the question that we came up with was, is it possible to compare man's current impact on the environment with those naturally occurring events which caused the great mass extinctions, of which there are 5. Now, to have a mass extinction, you've got to have a large and biodiverse population of plants and animals in the Earth's biosphere. And the biosphere consists of 2 parts, the marine and the terrestrial. And of course the marine is and always has been bigger than the terrestrial one, and in fact life pretty well started in the sea. So these are the 5 great extinctions. 440 years ago there was there was little life on land. The land was pretty barren, rocky, dust bowls, ash and all that sort of stuff. And the plants that did grow were weedy little things. They couldn't grow more than about 3 or 4 feet high because they only knew how to add a few cells of cellulose to the end of the stems, which meant that once they got to 3 or 4 feet high, they keeled over and died. So we know there was an extinction because of the fossil evidence, but the reasons we can only conjecture. Now we come to the next one. Very late in the Devonian era, evolution underwent a crucial step called arborescence. And what happened there was that plants learned how to add an extra layer of cells to their structures. And they also learned to incorporate lignin into their structures, which meant they could grow very much taller. So trees eventually, as we know, can grow tens of meters tall. They can support huge crowns of leaves and foliage, hundreds of millions of leaves. And those leaves photosynthesize. They produce food and oxygen. And the impact of that was that the Earth's atmospheric oxygen content went up from about 15% to over 30%. The other thing is, when the leaves die, they drop off and add organic content to this soil that's beginning to form. That's very important because while the biomass in the seas has always been bigger than the biomass on land, once evolution really got going on land, we now have 5 or 10 times more different species of land animals than we do sea creatures. So, again, the end of the Devonian was a complicated thing in 1 or 2 stages, and the causes are not clearly identified. Then we come to these last 2, the Permian, Triassic and the Cretaceous. The Permian extinction was the greatest one of all time. 90 to 95% of all life was extinguished. Life nearly died. Now, what caused these things? Well, volcanism is the most likely cause, as I think it almost certainly did. It's circumstantial evidence, but clearly, to cause a mass extinction, you've got to have some cataclysmic event which completely wrecks the environment. Basically, volcanism represents a huge release of internal energy from the Earth. Now, my colleague Jim Parker mentioned thermodynamics yesterday. Thanks, Jim. I'm going to mention it again now. System thermodynamics are very important. When the Earth is going about its orbit and the sun's shining, we can think of it as an open system. We have a system barrier around the outside of the upper atmosphere. Energy can come in without let or hindrance. And this energy sustains life. But if we, just to look at the first law of thermodynamics, first law of thermodynamics says that you can transform energy from one form into another. A second law, those two rectangles are the same area to indicate we've got the same amount of energy, but the second law says that you get the same amount of energy after the transformation, but it's not all available to you. And that shows that there's only a small amount actually available. The rest is non-available. An increase in entropy, an increase in system disorder. Now, that might seem not very good. I mean, but think about a steam locomotive such as we used to use 50 or 60 years ago. You've got 100 tons of steel, you're burning that fuel, all right, it boils the water and produces the steam, which drives the thing, but the heat also warms up 100 tons of steel to a greater or less extent. That energy cannot be used. When the thing goes down the track, it dissipates it, it pumps smoke and steam out, it's all lost. Those locomotives are about 10% efficient at most. The same holds for life systems. We can think of life as it takes sunlight in, but then it transforms the energy into all sorts of different types, and different creatures live in different ways on this production of photosynthesis. So at the bottom, what we call trophic level 1, you've got the primary producers. These are the things like the grass and the plants that turn sunlight into food and oxygen. Oxygen is very important. I've already mentioned the arborescence business. Trophic level 2, you've got herbivores that actually live on the primary production. Now, only 10% of the food value of the primary producers is taken up and turned into food in the herbivorous animals. By food, I mean the bits of the animal that you can kill and eat. Where does the rest go? Well, it's like the loco. It goes in heat losses, it goes in waste production, excrement, it goes in driving all the systems that keep the animals going, and then of course what lives on the herbivores, you've got various carnivorous creatures, and each time you go up to the next trophic level, only about 10% of the energy is transferred. And if you think about it, that shows why modern industrial agriculture is absolutely nowhere near as efficient as it was in the days when the farmer had a plough. He didn't pile energy intensive weed killers and fertilisers and all the rest of it onto the land. He just planted the seed and harvested it. That's by the by. So life is it's a thermodynamic system, energy is transformed, and that's how it works. So right at the top, you've got the top predators, tigers, sharks, polar bears, and so on. For every tiger, there's probably 10 trillion blades of grass. So it goes up, and there's far fewer of these creatures at the top than are at the bottom. This just illustrates the point. This is something I found recently, a food web for the savannah in South Africa. You've got the above ground primary production, 470 grams per square metre per year, and then it goes to the herbivores, which are then fed on by, you've got grazers, browsers, grasshoppers, caterpillars and things, and then the predators live on those. But lost, 410 grams per square metre per year. In other words, you're down to your sort of the order of 10 or 15% efficiency with that. You're right. Now, I've mentioned about thermodynamics, the fact that with a closed system, I haven't mentioned this actually, if you've got an open system where energy can come in and drive things, if you have a closed system, it means that you're actually releasing internal energy from the system, and it can't get out. We've got the Earth's gravitational field. It can't escape, essentially. All the stuff that's produced can't get out. Now, whether it's produced naturally by a volcano, or whether it's produced by us digging up oil and coal and burning them, the same situation applies. So I thought about this thing, and I read Clive Oppenheimer's recent book on volcanoes and things, and most volcanoes are situated around the Ring of Fire. There's about 1,500 active volcanoes at the moment. But it's not those sort of volcanoes that are responsible for the mass extinctions. There's a special kind of volcanism which occurs very, very rarely. And what happens there is the Earth's core is very hot. On top of that, you've got floating liquid mantle. And on top of that, you've got the crust. And very, very occasionally, a region of the mantle in contact with the core gets superheated. And you get a large volume of superheated magma, which acquires buoyancy, and it floats up towards the crust. Now, while it's liquid, it's not like water. It's not low viscosity. It's very, very viscous. Think of golden syrup when it's cold. You put the spoon in and tremendous resistance. So for this great bolus of hot magma to float up to the crust takes literally millions of years. And when it gets there, it bumps up against the underside of the crust and spreads out to form a large mushroom head, possibly as large as 2,000 kilometers in diameter. And that's hot magma. So it starts melting and cracking, and eventually it makes a split and starts to pour out. Because there's so much of it, unlike a normal volcano, which might last a few days or even a few weeks, or even in extreme cases just a month or a few months, this goes on for year after year, decade, century, millennium, thousands of millennia. And when I read up about the thing that drove the Permian extinction is a thing called the Siberian traps. There was a huge eruption of magma in Siberia. We can now scan those with the old digital technology and estimate the thickness. And according to Oppenheimer, there's something like 2 million cubic kilometers of lava in Siberia. So I thought, right, well, we know the physical properties of basalt. According to Oppenheimer, it comes out of the ground at 1,100 degrees C. Work out the volume, and know the density, work out the mass, work out the specific heat capacity. It's possible to calculate the energy output in joules. What triggered the conversation with Chris was I just calculated the energy release when the Chicxulub meteorite crashed into the Gulf of Mexico, and that was the event that most people think finished off the dinosaurs. However, at the same time that happened, there was another big eruption of magma in the Deccan in southern India. So we've got the Siberian traps 250 million years ago, and the Deccan traps 66 million years ago. They're called traps because derives from the Swedish word for steps. When the lava solidifies, it forms steps. So I got the volumes of these, and I was able to work out some energies. Now, what about the Triassic? Well, the Triassic extinction occurred about the time that the North American landmass hived off from Pangaea, and the Atlantic Ocean flowed in to fill the space. And these large igneous provinces, or basalt floodplains that come out due to this particular very rare form of volcanism, one of those occurred under the North Atlantic. So that meant that this Triassic extinction was a marine event. It affected marine life more than land life. the earliest dinosaurs were walking around before the Triassic extinction, so they obviously survived. After I've done all these calculations, I've got a series of energy values which are shown here. Now, these are the sort of initial results of the calculations. I'm still writing this thing at the moment, and I want to go back and revisit some of these figures. But total energy release 5.72. The 5.72, as an engineer, I give no credence to that. It could be 2 or it could be 9. The important bit is it's 10 to the power 24 yotta-joules, a million joules. You get a similar thing for the Deccan and the Chicxulub wide, and again, nobody knows how big it was. It's thought to be either between 6 or 9 miles in diameter. It could have been doing 20 kilometres a second or 30 kilometres a second. I came across some figures in a book that was published only 3 weeks ago, which showed that my calculation, each started off from a slightly different viewpoint, but his energy calculation agreed very closely with mine. Now then, there's a guy in America called Václav Smil, and he spent his entire career dealing with matters of energy. How much energy does a sailing ship use? How much energy does a railway engine use? All this sort of stuff. How much energy does a person consume to do a day's work? And he's just full of data on energy, and he's got a figure for the average per capita consumption of energy on Earth for each person. And so I've used that for the anthropic energy global consumption. And again, I've got a figure that the middle column is the total energy release. The right-hand column is the annual energy release rate in joules per year. And again, you notice that the two volcanic events, the units are exajoules, 10 to the power 18 joules. For the Chicxulub meteorite, it's not applicable, but for the anthropogenic energy production, I've got 500 exajoules, half a zetajoule, if you like, but it's the same sort of figure. The thing is that what it comes down to is the fact that as things are now, we are pumping into the atmosphere, energy at the same rate as happened with these naturally occurring events. Now, I've put this figure in because there's 2 ways you can deliver energy. The Chicxulub meteorite delivered it all in one blob. So you've got a sort of step function put into the system. The way we do it progressively, and the way that the Siberian traps and Deccan traps did, was in a progressive way, a ramp function. And if my figures are correct, which they may well not be, the actual numbers, but the orders of magnitude are right, it could take 100 or 200,000 years for the Siberian traps to deliver the same energy that the Chicxulub meteorite put in just a few seconds. So what does that say for us? Well, we are obviously, with our rate of output, we're approximating more to the ramped function, except that, as we all know, we're doing it at an accelerating rate. So it's not a linear thing, a linear ramp, it's an upwardly curving ramp. Now, that means that we're undoubtedly in a danger zone. We're putting energy into this closed system at a rate which, long term, could cause another mass extinction. So the answer to the question is, yes, we could be heading to another mass extinction. Now, I like to sort of finish on a more optimistic note. when I started teaching the subject of sustainability many years ago, I came across the work of a bloke called Friedrich Schmidt-Blake in the Wuppertal Institute in Germany. And one of the indices he devised for measuring impact was the idea of ecological rucksack, or in other words, how much material do you need to dig up, say, to make a ton of steel? Well, I think the answer was about 10 tons. So you dig up 10 tons of iron ore, 10 tons of coal, 10 tons of limestone, and you shovel it in, and you get ultimately a ton of steel. So 9 tons of that represents waste. That's 9 tons of entropy added to the system. The Chicxulub meteorite obviously caused an energy release because it buried itself in the earth, and a load of ejecta came out, and that will have had a pretty devastating local effect. Added to the Deccan traps, that was what undoubtedly caused the end Cretaceous extinction. So, is there anything we can do? Well, the thing about Schmidt-Blake's ecological rucksack idea is some materials you have to dig literally hundreds of tons of material out just to get 1 ton. And it seemed to me, instead of worrying about the embodied energy of materials, shouldn't we be taking more notice of the second law of thermodynamics, which talks about increasing entropy? Shouldn't we be trying to use materials which produce the smallest amount of waste in their production? That's something that we could do. The other thing that I thought of was something that somebody mentioned, that the guy from Yemi Construction, who was talking about the material that would actually absorb pollution and produce oxygen. Biomimetic materials. In other words, oughtn't we to look at the way, even more at the way nature works, and see how nature deals with problems? And what he was describing sounded to me like a biomimetic material. If it would do that sort of thing, it was actually mimicking something that photosynthesis does. So those are a couple of things I think that we ought to take a note of. Trying to use materials that produce less waste. I mean, the other thing is, Neve Murtaugh mentioned the Attenborough programme, and she showed that image of the floating plastic. That represents part of the increase in entropy to the system. But what David Attenborough also showed was the floating carcass of a 30-ton whale which had been killed by a passing container ship. And he also showed what happened to that carcass. All the fishes swam towards it, but everybody held back until a great white shark had eaten his fill, because you don't mess with great white sharks. And then the other sharks moved in, and they all chobbled away until what was left sank down into the inky depths of the ocean, from the photic zone into the benthic zone, where there's no light. When it got down there, populations of crabs and other creatures tucked in, and when there were just the bones left, the whole population of worms came out of the mud and finished off the skeleton. So within 4 decades, nature had cleared up its mess. And the important thing is that things that clear up the mess are solar powered. They don't. Nature, this is it, there can't be an increase in, as long as it's an open system, there can't be an increase in entropy, because the natural systems will make sure that it's all set up so that dead material is the food for other creatures which feed on it and clear it all up. So there's no mess out there. Whereas what we do doesn't do that. So we need to look at what we can do towards possibly devising mechanisms which clear up the mess, if you like. And so there's a couple of areas there that I think are big fertile things to look at. And I think that's just about all I've got to say. So thank you very much for your attention.